Okay, hello everyone. I'm very glad to be here and talk about some other ophthalmology applications. Dr. Kudros definitely gave a very wonderful presentation on the diagnosis for the retina diseases through the telemedical links. In my lab in Davis, we are focusing on a particular ophthalmology problem, glaucoma, and we'll share some story and some of our technology developed over the last couple of years. Here is a cartoon of the cross-section of the eyeball, and as you can see here is retina, and the retina collected all the nerve fibers and connect the backside and exit the eyeball through the optical nerve bundle. And in the main chamber of the eye, you have two chambers. One is the posterior chamber, and the forward one is the anterior chamber. So for glaucoma patient, regularly they have the they have a fluid called aqueous humor. It's generated through the blood vessel, through the cornea, through the cilia muscle here, and it flows through the pupil into the anterior chamber. Then it drains out through the trabecular meshwork into Schlemm's canal. Here, the cross-section view actually is one cut through here, provide another view about this fluid problem. So that's how, as an engineer, I envision this problem. They got the flow comes through a corner, actually is the backside of the lens, and through the pupil and into the anterior chamber and filled up. And then they have a ring structure of a nanopore structure around, and this aqueous humor flows through this porous structure, getting into the correct channel. And eventually, this fluid comes back through the correct channel to the venous circulation system. So the glaucoma happened because of the flow blocked somewhere along this fluidic path. So the pressure actually elevated due to the increase of the resistance. So break down this picture, and the glaucoma actually lead to the #1 irreversible blindness in the world. So total glaucoma patients in the world is about 7 million people, and more than 10% of them are blind in their both eyes. So currently there's no cure, and the current treatment cannot fully stop glaucoma progression. So clinically, people are looking for better diagnosis and the treatment system. Here is what we are doing in our lab, and so we are trying to look at a different aspect for this disease. So first, we're thinking, okay, this is a problem where you got the resistance increase in your drainage network. So how about if we include a new drainage network, which can replace the dysfunctioning or disease network and let the eye flow drain better? Okay, there are a couple of approaches we are looking at. We can look at the flow drains through the trabecular meshwork, and we replace the meshwork into an artificial meshwork, and let the eye flow come through the transsclera and directly get into tear film. But the challenge in this work actually is because we open up a new drainage pathway instead of go back to the venous circulation system. We have to have this guy exposed to the environment. So which lead to you have to build an artificial immune system to prevent the bacterial infection. And the second thing we're looking into in the eye is actually that's another thing linked to ophthalmology is macular degeneration. So that's another leading disease of blindness. So you actually can do the drug delivery. I mean, for drug delivery, you have to overcome the barrier. I mean, if you deliver drugs through your cornea directly, actually the aqueous humor circulation will flush your liquid directly drain into your circulation network, so it would not work. And what you are looking at is you want to have some drug can transsclerally and perfuse this through your membrane and into the eye, and either can do the anterior drug delivery or posterior drug delivery. So we are also looking at controlled drug delivery chips can be implantable or can be also biodegradable into the body to perform long-term drug release. Another thing is currently people always believe the pressure is most indication for glaucoma, and also over the last couple of years, over last couple of decades, people are still using the traditional method which they poke, metallized the pen towards your eye and measure the force, interact with the cornea to measure the pressure. So we're considering building, new device, use more, biocompatible material and also highly sensing mapping device to retract the information inside of the eye. So including the pressure information and the flow information. And more, what we are looking at is actually what happening really at the optical nerve head. So the problem has been, people always measuring the pressure, but it doesn't really know what the pressure impacted the optical nerve head. So our approach is really combined the biomechanical approach and the imaging approach, really telling the story what's going on with the optical nerve, why somebody has high pressure, they don't have a glaucoma progression, but someone even with 15 millimeter mercury, they are going to lose their vision in the retina. So this actually, here I show the first generation of the glaucoma artificial implant we developed 3 years ago. And this actually is fabricated by the conventional microfabrication technology, which make the same thing for the computer chips. We can use like a 4-inch standard semiconductor substrate, manufacture thousands of these devices. Each of them is about 1 centimeter in diameter and connected to a biomedical tube to drain the eye fluid. And this is the nanoporous membrane we fabricated as a bacterial barrier to prevent the bacteria getting into the system. So each of the pores is about 100 nanometer wide. The problem actually with this first generation device was because it's based on silicon technology, and the surface coating we put on is a biocompatible surface, polyethylene glycol polymer. That one doesn't really prevent that one is not good enough to prevent the proteins clogging into the channel. So currently we're working on pure polymeric substrate to hold on the whole device, and looking forward to moving to animal testing. And the other things here is scanning scope, scanning electron microscope of the optical nerve head. By taking the nerve fiber away, it shows up the collagen fiber structure. That's what happened when the nerve head exists to the eyeball, just like in this picture, this structure here. So this supports the optical nerve fiber bundle. So under the elevated intraocular pressure, this guy has been compressed. So the optical nerve fiber is getting compressed and not able to do efficient the mass transportation and the signaling, so they gradually lose their function. So we're trying to take this anisotropic biomechanical property into the consideration and building the network of understanding of the collagen fiber network, and trying to combine the imaging, different imaging modality to understand how the in vitro the biomechanical deformation goes on with the elevated intraocular pressure. Another thing is we are building this flexible robotic mapping device, trying to understand the biomechanics inside of the eye. So we're hoping in the next couple cycle of the development, and we can really help to understand better what's going on with the glaucoma, and we can design better strategy to really regulate the intraocular pressure and the aqueous humor outflow. Thank you.
Thank you very much, Dr. Dan. In the